This is tutorial 8A question 5. The question is this. We're given a time sequence X, 4 sample time sequence X, small x, that has 2003 as its value. And we are asked to find xk, capital X, via DFT method. Now, this is redundant. Well, maybe not redundant. Here we specifically ask for n equals to 4. And this matches to this sequence here. So, to find the capital X, basically from a linear algebra perspective, the small x is being transformed by a DFT matrix W. And this is input is a 4 by 1 vector, and DFT matrix is a 4 by 4, and therefore the output is a 4 by 1 matrix. The notations is very important here. The small x is the time input, the capital W is the DFT matrix, the capital X is the DFT coefficients. Now, you'll see in many books that the DFT coefficients have index k, and it'll be 0 index up to n minus 1. So it's k equals to up to n minus 1. And similarly, the index for x is small x 0 until x, small x, n minus 1 over here. So, therefore, if you can view this notation, then the notations for the W matrix, W is a square matrix, the notations or the index for the W matrix must be observed in this form. Since X is a column vector indexing from k equals to 0 to n minus 1, across the rows of the W matrix, it is the similarly indexed as k equals to 0 to n minus 1. What about here? The small x is indexed from small n equals to 0 to n minus 1. Therefore, the rows of W, the elements of W in the row must be indexed from n equals to 0 to n minus 1. Remember this, and you'll figure out that it is actually the rows of W operating on the x factor to produce one element of the capital X. The corresponding row of W, the kth row of W, inner producting with the small x will give you the corresponding capital X kth element. That's the key idea. The second thing to remember is this. The W matrix, the elements of the W matrix looks like this. Every element is e to the power of minus j 2 pi over capital N kn. So you'll be able to substitute the different k's and different n into this kn over here. Actually, it doesn't matter whether I write nk or kn. This is commutative, and you'll realize that the DFT matrix is symmetrical. The minus is important, okay? Now, with that, once you understand this, you understand that to solve for the DFT approach for small x, then simply you fill up the W matrix. But we do not need to fill up the W matrix. Why? It's because we can recognize that it is the non-zero element of small x that will be can be multiplied by the columns of k. So it is 2 multiplied by the first column of W. It is the non-zero element of small x that will be multiplying with the corresponding W. So it's x0 multiplying the first column of W, column 0, as well as the last element, which is x small x of n, capital N minus 1. We'll be multiplying with the column 3. So in a matrix vector multiplication, you will be more useful to imagine that it is the elements of this small x multiplying with the corresponding values of W, corresponding columns of W. Now with that, I sketch out this corresponding column of W for column 0. This is column 3. So this is the coefficients from x. And then I can fill up these elements. And how to fill up these elements? Remember just this equation over here. So that's the way to do it. And this is the answer for question 5. Now, for the theory, this will be the theory in our lecture notes. The details are here in page 20. The capital X is the DFT coefficients, the X is the input, the W is the DFT matrix, and the elements of W is here, the minus sign here. Okay? And this is the thing that you'll see. Again, I repeat, in the capital X, the element starts from 0 and ends at n-1. We call it the DFT coefficient, capital X. Here, the input, the elements are indexed small n equals to 0 until small n equals to n-1. So you see this green arrow going down. Now, to make the notation consistent, we are inner producting each row with this each column. Therefore, this guy, the elements must be indexed by n. Then if we are finding capital X1, we are using this row, right? Inner producting with this guy. Therefore, in the DFT W matrix, the index appears to be going down this way for K. Right? With that, then we have reviewed question 5A. Thank you.